Hello everyone, welcome to Augment Tech. In this session, we will be learning about Python Seaborn, histograms, and kernel density estimates. By the end of this session, you should be able to understand what is an histogram, what is KDE, fitting parametric distribution, and kernel density estimation. I'm excited to get started and hope to see you from you. Let's get started with histograms. Histograms represent the data distribution by forming bins along the range of data and then drawing bars to show the number of observations that fall in each of the bin. So here we first import pandas as PD, cborn as SNS, and then matplotlib, a pyplot as PLT, and then we'll be loading the data set, iris data set using a cborn, and then we'll be plotting a dist plot on one of the column of the iris data set like petal underscore length. So this plot here is used to show the distribution of univariate set of observations, and then here we have a parameter KD equals false. So let's have a look at the output. There we go. This is how the plot looks like. So here we have a petal length and the histograms are plotted, and we do not have KDE, meaning we do not have the curve of KDE, that is kernel density estimation, as we specified the parameter KDE equals false here. Now let's understand what is KDE. So KDE here is kernel density estimation. It's a way to estimate the probability density function of a continuous random variable, and it is used for non-parametric analysis. So here we setting the hist flag to false in this plot will yield the kernel density estimation plot. So once we specify hist equals false, we will be getting a plot that will have only the curve for the kernel density estimation. There we go. So here we import pandas as PD, cborn as SNS, and then matplotlib as PLT, and then again we will be plotting the same this plot on petal underscore a length column of the iris data set, and when we say hist equals false, there we go, you see this only plots the KDE. This curve represents the kernel density estimation. And if you do not specify anything, either KD equals false or hist equals false, it should be plotting both histogram as well as the kernel density estimation curve. Now let's see what is fitting parametric distribution. So this plot is used to visualize the parametric distribution of a data set. There we go. This is how the output looks like when we do not specify KDE equals false or hist equals false. So you can see here we have histograms as well as the curve for kernel density estimation. Again, this particular plot is for the iris dataset available in cborn. Now let's have a look at kernel density estimation. So kernel density estimation is a non-parametric way to estimate the distribution of a variable. In cborn, we can use joint plot to plot a KDE. Here we can pass the value KDE to the parameter kind to plot kernel plot. So again here, the joint plot is going to match two displots and then show the distribution of bivariate data, and we can specify the parameter kind to it, passing value KDE to it. There we go. So here we import pandas as PD, cborn as SNS, matplotlib as PLT, and then we load this iris data set. So here you see we have two columns, x equals petal underscore length, y equals petal underscore width. Data, that is the data set's name, we have to pass iris, and then kind equals KDE. And there we go. This is how the output looks like. So here we have on the x-axis petal underscore length, on the y-axis we have petal underscore width, and then you can see the plot is actually KDE plot. Now let's hop to Jupyter Notebook and check out the example of histograms and kernel density estimates. I'll see you there. Alright, so here I'm on my Jupyter Notebook under the C1 folder inside Python data analysis folder. I'm going to create a new Python notebook and let's name this as histogram and KDE. So here I'm going to rename this one to histograms and let's specify the heading here saying histograms and KDE. And let's first discuss about histograms, like what histograms are. So here I'm gonna write a heading saying histograms. And then a markdown here. So here I say histograms represent the data distribution by forming bins along the range of data and then join bars to show the number of observations that fall under each bin. Now here we'll be importing all the required modules like import pandas as PD and then import matplotlib.pyplot as PLT and then import Seaborn as SNS. So Seaborn comes with built-in datasets. So we'll be using one of the datasets known as Iris datasets from Seaborn. So here, let's create a data frame out of it. I say iris equals sns dot load underscore dataset, and then the name of the dataset is iris. And then I'm gonna do iris and check. There you go. This is our iris data set having 150 rows and 5 columns. And the column names are sepal length, sepal width, petal width, and species. So now I can go and do just iris start head in order to see the first 5 rows, and I can do iris dot tail in order to see last 5 rows. I can also do iris dot info to get the information about the data set, like if the data set is having any null values or the data types of the columns, and there we go. So in our data set we have non-null count 150, so it means there are no missing values. Columns are sepal length, sepal width, petal width, and species. And the data types here are float 64 for all the columns except for the species. And species here is a string column, or in other words, it's an object. You can also do iris.describe in order to get the descriptive statistics for this data set. So it will exclude the species column and then give the descriptive statistics for all the numerical columns. Let's go and see. There we go. You see for simple length, petal length, petal width, it's giving us all these values like count, mean, standard deviation, minimum value, maximum value, 25%, 50%, and 75%. Now let's plot this plot that should be taking hists, or that should be plotting the histogram for univariate set of observations. So here I do import matplotlib dot pyplot as a plt, and then import cborn as sns, and then iris equals sns dot load underscore dataset, and then let's say it's iris dataset. Iris dot head. Alright, so what I'm gonna do here is I'm gonna do sns dot distplot and then dataset name, and then we'll be plotting on petal length column and then specifying KD equals false. So this should not be giving us the kernel density estimation curve when we do so. So now if I go and run, you see I actually get a warning for this plot saying that it is depreciated, but here you can see the histograms. It's plotted. I can also specify bin here. Like for example, if I say bin equals 30, should be bins equals 30, and there we go. This is how the output looks like. So let me remove this warnings, or let me ignore this warning by doing something like this. I'm going to import warnings and then warnings dot filter warnings and ignore. Let's run this cell and also run this cell. There you go. This is how the output looks like. Alright. Now let's understand what is KDE, or kernel density estimation. So here I'm going to write a heading saying kernel density estimation. So here I say kernel density estimation, and a markdown that says kernel density estimation, also known as KDE, is a way to estimate the probability density function of a continuous random variable. And it is used for non-parametric analysis. So the same iris data set, I'm going to do SNS dot distplot, and to this I'm going to pass iris of, let's say, petal length, and then I'm going to specify hist equals false so that I can only see the KDE plot. There you go. This is how the output looks like. So when you specify hist equals false, you should not be seeing the histograms on the plot, Instead, it is only showing us the KDE. So this curve actually represents the kernel density estimation, which is a way to estimate the probability density function of a continuous random variable. Now let's see how to fit the parametric distribution. So here I see, let's say this is a markdown saying fitting parametric distribution. So this plot is used to visualize the parametric distribution of a data set. So here again I can do rs equals this plot and then rs of, let's say, petal length column should be sns.displot, and there we go. This is how the output looks like. So when you do not specify any parameter as KD equals false or hist equals false, you should be seeing both the histograms and the kernel density estimation curve on the dist plot. So this is known as fitting parametric distribution, wherein the dist plot is used to visualize the parametric distribution of a data set. Now let's have a markdown here that says kernel density estimation is a non-parametric way. So here I say kernel density estimation, or KDE, is a non-parametric way to estimate the distribution of a variable. And in Seaborn, we can plot KDE using joint plot. Now let's see how to do that. So here I'm going to first import pandas as pd, import matplotlib dot pyplot as plt, and import Seaborn as SNS. And then let's load the data set here. So here I see iris equals sns dot load underscore data set. Iris is the data set. Iris dot head. Let's quickly go and check. Alright, so here I'm going to do sns dot joint plot to which I'll be passing two column names, one to the x-axis, the other to the y-axis. So here I'm going to say x equals and y equals, data equals, let's say, the data set name or data frame name iris, and then kind parameter, let's say this KDE. Now let's say here to the x will be passing petal length, and to the y will be passing petal width column. So here the joint plot is actually matching up the two dist plots and showing the distribution for bivariate data. So let me quickly run. There should be joint plot. And there we go. This is how the output looks like. So to this, we don't actually need to specify hist equals or false. So this is how we can make use of a joint plot plot a KDE, that is kernel density estimation. Right guys, so this was about histograms and the kernel density estimation on the iris dataset available in CVOL. So that's all for this session. Hope you enjoyed the session. We'll see you in the next.